All right, here we are, right where we left off. I haven't even moved. I moved what was on the screen. I didn't move, I didn't go anywhere. Because I want to talk to you about symmetry, and this conversation is where things start to get a little detailed. So, hopefully, you have the attention span at the moment to make your way through this with me. It's not actually all that difficult, but it's not even conceptually that difficult. It's just kind of a lot of stuff. You'll see. So symmetry with respect to the polar axis, which formerly known as the x-axis, in order to test to see if a graph has symmetry about this horizontal axis, we can take the theta value in our polar equation and replace it with negative theta. I've highlighted that right down here. And if after making that replacement or that substitution, if we can then abide by the rules and manipulate that resulting equation to the point where it looks exactly like the original equation, then the graph of that equation will exhibit, in this case, polar axis symmetry. So if you can make the substitution and then convert the equation back to be identical to the original, then the graph is going to exhibit that kind of symmetry. If an equivalent equation results, the graph is symmetric with respect to the polar axis. Okay, so that's how it's phrased in print there. Now, the second test is to see if we have symmetry with respect to the line theta equals pi over 2. In other words, symmetry about the y-axis. And we can test to see if that is the case. And I don't love this diagram, actually. It sort of works. I don't love that this dashed line is here. I really just wish that this one was here. Or maybe I should have highlighted it in blue. No, because now it's blue on blue. Oh, that's okay, that worked. So when you take the solid blue line that's in the first quadrant and you reflect it over the line theta equals pi over 2, the y-axis, you end up with that dashed line in the second quadrant. How do you test to see if a graph is going to exhibit this kind of symmetry? You replace r and theta with negative r and negative theta respectively, and if you can convert the equation back to the point where it's identical to the original, then the graph will exhibit that kind of symmetry. And thirdly is pole symmetry. Symmetry with respect to the pole. You test for that by replacing r with negative r, and if you can make the new equation end up looking exactly like the original one, the graph of that equation will exhibit pole symmetry. Now here's the kicker. This is something that you're liable to forget, so if you haven't highlighted anything ever, highlight this. If you do one of these tests and the equation fails that particular symmetry test, that doesn't mean anything. The graph could still exhibit that kind of symmetry. It might not, but it might. So if you fail a test, if you fail one of these 3 tests, you haven't really learned anything. It's only a sure thing if you pass the test. Let's try them, okay, using this equation. We're going to test for all 3 types of symmetry. These tests require a few steps, so what I'm going to do is try to do one test here and one test here, and then I'll try to squeeze another test sort of in here. I might have to go into the margin a little bit though. So if you tend to write kind of large bubbly letters and numbers when you take your notes, try to make them small bubbly letters and numbers this time, because otherwise it might not fit. Or you could attach a separate piece of paper, but I think you can do it. Let's see. Well, for that matter, you could fast forward in the video and see how much I end up writing in here, and then you could decide for yourself whether or not you can make it fit. I'm going through all this because it's important that you be able to take legible, well-organized notes where you can have room to put in some little annotations and things like that so you can understand your notes later. So That's why I'm encouraging you to fast forward and just see what these notes look like. Okay, so which test should we do first? Let's do them in order. So we're going to test for polar axis symmetry first, replacing theta with negative theta. Let's see. Polar axis symmetry. We test by letting theta equal negative theta. And I don't like that. I'm not going to put parentheses around them. I'll tell you why in a minute. We're going to let theta equal negative theta. That's an 8. There we go. Okay, so let's make that substitution. So now we have r equals 1 minus 2 cosine, not cosine theta, now it's cosine negative theta. So here we've made the substitution. The question is, can we convert this equation back to look exactly like the original? And the answer is yes. Because cosine is even, comma, r equals 1 minus 2 cosine theta. This looks exactly like the original equation. Therefore, the graph will exhibit polar axis symmetry. I'm not going to write that down. If you can fit that maybe right here, looks exactly like original. Therefore, graph will have polar axis symmetry. Okay, I'm going to let you write that in right up here. You should be able to fit it in a couple lines, and below that I'm going to do my next symmetry test. Let's test for, I believe that one is theta equals pi over 2 symmetry. We test for that by letting r and theta equal negative r and negative theta. There you need to be using parentheses, not over here. Now, you know, if I were typing these up, I would put them in bold or something. If you want to underline them, if you wanted to, maybe you could highlight these, polar axis symmetry, and that's what we do in order to test it. Here's this kind of symmetry, here's what we do in order to test for it. That's not a bad idea. And then stuff that's not highlighted is us actually doing the test. Okay, so I'm going to replace r with a negative r equals 1 minus 2 cosine, and then replace theta with, negative theta. Now we already know that on the right hand side of this equation we can change the negative theta to a positive theta because cosine is even. So for starters, let's do that. And if you want to write it again, you can. Because cosine is even, comma, negative r equals 1 minus 2 cosine positive theta. The problem is the negative r. There's no way I can remove the negative from the r. I can't just erase it because cosine is even or something. And if I multiplied both sides by negative 1, this would become positive, but this would become negative, this would become positive, and the equation would not look like the original equation, which is the goal. So it appears that we're stuck, and however you want to phrase this, can't make to look like original, or to look like r equals 1 minus 2 cosine theta. However you want to write it, remember, whatever's going to make most sense to you later. Since we can't make it look like the original, maybe just write fail. Over here, we can write pass. Depending on what you wrote in there, if writing the word pass up there is helpful, then you should write it in. Okay, the last symmetry test, we have pole symmetry. We test for pole symmetry by letting r equal negative r. We'll hit it with the highlighter. I don't know why that did that. There we go. And there. Nice. So replacing r with negative r gives us negative r equals 1 minus 2 cosine theta. Oh, well, look, this is exactly the same as this troublesome situation that we were in. There's no way to take this equation and make it look like the original. So either you can write that out again, or you can write fail again. Right, that's what I'm going to write. Fail again. Now remember that when you pass a symmetry test, the graph will exhibit that symmetry, that type of symmetry, for sure. So this graph that we're about to draw will definitely have polar axis symmetry. It may or may not, however, have theta equals pi over 2 symmetry, and it may or may not have pole symmetry. Because those tests failed, or because the equation failed those tests, we didn't glean any knowledge from that. Okay, still may or may not exhibit those kinds of symmetry. Now I've already filled in this table for us. Let's plot these points. Aiming in the direction of 0, I will move -1 unit, so in the direction of pi, and I'll plot a point there. Aiming at pi over 6, I'm coming back approximately, well, it's sort of like 3/4 maybe. About there. Aiming at pi over 3, I'm not going anywhere, so I've got a point at the pole. At pi over 2, which is due north, I need to move toward pi over 2 1 unit, so I'm going up 1. Aiming at 2 pi over 3, going out 2 units. 2 pi over 3 is, yep, there it is. Going out 2 units. At 5 pi over 6, I'm going out something like 2 3/4. And aiming in the direction of pi, I'm going out 3 units. So I plotted all of those with solid dots. And the next thing I'm going to do is use the fact that I know that our graph passed the polar axis symmetry test. So the graph will exhibit polar axis symmetry, which means I can take each one of these points and reflect them over the horizontal axis and plot a point there also. I have this technique that I use. Technique makes it sound fancy, which it's not. If I'm going to plot a reflected point, I plot it with a little open circle, and that tells my eye that I've plotted a reflected point. So let's take, and I'm going to take this point, reflect it over the horizontal axis, and plot a point here. And then I'll take this point and fold it over. So let's see, that's going to be down here at 2, okay. So I just plotted in the direction of 4 pi over 3, and I'm out 2 units. Now let's take this point, reflect it over, puts us here. Then I'm going to take this point that was below the horizontal axis, or the polar axis, reflect it up. So I do get an open circle there. You could put open circles around these. I think that just makes for clutter, so I'm going to not do those. And I'm going to draw the first part of this graph in the order that I plotted the points. So I'm going to start here, and then I'll go to here, and then I'll go to here. So let's see them as they play out as we move from a theta value of 0, and then with increasing theta values. I should have zoomed out before I started doing this, otherwise I'm going to have to move my hand a whole bunch of times. Okay, finished a little rough. Oh, look at that, I had to erase all of it. What I want to point out to you happens right here. As I draw the rest of this graph, it should move into the fourth quadrant just a little bit before coming back in and closing this loop, which means that the part that's in the first quadrant, let's see if we can erase it and make it look just a little bit better. I'm going to come in here and just really try to get this to push into the first quadrant a little bit. Okay, that makes this transition look a little gnarly, but that's okay. So that is sort of a defining characteristic of this graph, is that not only does it have this inner loop, but it does protrude a little bit into the first and fourth quadrants. All right, so we didn't have to plot quite so many points because we were able to use the symmetry that we knew that this graph would display. Let's just take note of the fact, does it actually show theta equals pi over 2 symmetry? Is this graph symmetric about the y-axis? It is not. What about pole symmetry? It does not exhibit pole symmetry either. So as it turns out, failure there meant it didn't show them, but that was not a guarantee. We had to discover that for ourselves by drawing the graph. Okay, that's our conversation about symmetry. And actually what we've just drawn here, this particular type of a graph, is called a limicon. And so you can see at the bottom of the screen limicons. I'm going to do a fairly quick but in-depth conversation about limicons in the next segment of this section. So if you would please click on the link that is right below me, I would appreciate it, and we'll continue this conversation with a little chat about limicons. See you in a second.